Welcome to Tomorrow Unveiled, your weekly deep dive into the innovations that are actively reshaping the human experience.
And this week, the sources compiled by our dedicated research team show something much more than just a typical tech news cycle. We are, I think, witnessing a fundamental shift in what a wearable even is.
Absolutely. Think back over the last decade. For most of us, technology was all about the quantified self.
Right.
We wore smartwatches, fitness trackers, and they were basically passive data collectors. They'd count your steps, track your sleep, and then give you this, clean summary of what you already did.
That whole era,
Yeah.
it's definitively over. The convergence we saw this week, specifically from November 19th through the 26th, 2025, it really signals a move into what our team is calling the strapped-in paradigm.
Strapped in, I like that.
It's because these devices are no longer just observing. They're actively integrating. They're augmenting our cognition, restoring lost functions, and merging with our very physiology through these high bandwidth computational loops that are happening in real time.
So it's moving from tracking to actual symbiotic augmentation.
Exactly.
And our mission today is to unpack the source material that really validates this shift, focusing on three major areas of convergence that accelerated, dramatically this week.
The first is what we're calling neural convergence. This is the huge leap where high bandwidth connectivity is pushing brain-computer interfaces, BCIs, out of that realm of just simple cursor control,
Right.
and into the really complex real-time demand of synthetic voice restoration.
Okay, and second.
Second, we have haptic convergence. Touch feedback has, it seems, finally crossed the threshold of human resolution. We're going to explore how material science is closing that famous touch gap in digital environments, making it possible to actually feel texture.
And finally, a big one, market convergence.
A huge one. Smart glasses have reached a key inflection point. They're hitting their mainstream smartwatch moment.
And that's all being driven by manufacturers finally solving that critical problem of intuitive, hands-free input. So this deep dive on Tomorrow Unveiled is really designed to show you not just what is happening, but why this moment is so pivotal. It feels like the true dawn of human-machine symbiosis. Let's get into it.
Okay, let's start with the brain, because the speed of integration here it's just staggering. The core story really revolves around these BCI breakthroughs, particularly the race to restore speech.
Yeah, what really stands out in the compiled data is the regulatory approval. Paradromics, a huge player in neurotech, they received FDA Investigational Device Exemption, or IDE approval for their clinical study.
The Connect One study.
The Connect One study for the
Right.
Kenexus brain-computer interface. And that came through on November 20th.
An FDA IDE is a massive green light. It signals that the device is, safe enough to actually test in humans. But why is this specific trial, Connect One, such a game changer compared to what we've seen before? It's the focus. It's because of its explicit focus.
Yeah.
This is the very first BCI trial that's been sanctioned that is explicitly designed to restore speech through real-time synthetic voice generation.
Not just moving a cursor.
No. All the previous landmark BCI work, the headlines most people remember, they were focused on motor control, moving a cursor, controlling a prosthetic limb.
Which is complex in its own right.
Oh, incredibly complex. But restoring fluid, natural conversation, that requires an exponentially higher level of fidelity and speed.
Okay, so when you say speed, are you talking about just the sheer volume of data, or is it more about the responsiveness, the latency required to process all those complex patterns of intent? This is really the core of the bandwidth war, right?
It's both. And the two are completely intertwined. You need both volume and immediate responsiveness for speech. If you look at the industry benchmark for competitors who focused on basic cursor control, the data transfer rates, they call the information transfer rate, or ITR, it's often around 10 bits per second.
Which is fine for slow typing.
It's adequate for slow typing or clicking, sure.
But the sources noted a radical difference with this Kenexus device.
Exactly. The Kenexus Breakthrough, benchmarked in preclinical settings, hit a performance exceeding 200 bits per second.
Wow.
That is a 20-fold jump in raw throughput. This high ITR is absolutely critical for decoding the incredibly complex neural signatures you need for fluid, real-time speech.
If you don't have that bandwidth.
If you miss that bandwidth, you don't get conversation. You get fragmented, delayed output. It's the difference between old dial-up internet and fiber optics, but for the brain.
That analogy perfectly illustrates it. It's the difference between translating a single command versus the nuance of a whole conversation. So let's get into the technical detail. How do they actually achieve that kind of throughput? 200 BPs requires a pretty specialized implant.
Well, the Kenexus design it's robust. It uses a high-density penetrating array. And this array, even though it's only about 7.5 millimeters in diameter, it packs over 400 platinum iridium electrodes.
And these don't just sit on the surface, right? They penetrate.
That's the key. They penetrate the cerebral cortex by about 1.5 millimeters.
So they're getting much, much closer to the source signal of the neurons themselves.
Precisely. They are recording single-unit activity, the actual firing of individual neurons, rather than just the aggregated electrical noise that surface sensors pick up.
And that granular data is what unlocks the high fidelity needed for speech.
It has to be. You need to read hundreds of distinct conversations happening in the speech centers of the brain all at the same time.
That is a huge amount of data being generated right there at the source. And getting that data out safely, efficiently, that has to present massive engineering challenges. I'm thinking thermal heating, infection risk.
And they had a very clever engineering solution for that. So the cortical implant module, it links via a short wire under the skin to a chest-mounted transceiver. Think of it like a pacemaker in terms of size and placement.
Okay.
But the key innovation our research team highlighted is the use of an optical link fiber optics from that chest transceiver to the external device.
And that design mitigates the major risks.
It does. High bandwidth radio frequency, or RF, transmission can actually cause thermal heating of sensitive neural tissue. That's very dangerous. The optical link drastically reduces that risk.
And the infection risk.
Gone. Because you're keeping the entire connection under the skin, you remove the risk that comes with physical wires passing through the epidermis. It's basically an invisible, low-risk highway for massive amounts of data.
So this FDA approval, it really formalizes what's become a highly competitive BCI landscape. The sources are calling it a tripartite competition.
Yeah, you really have three distinct strategies emerging now. First, you have Neuralink. They're focused on maximum density with their penetrating threads, aiming initially for general PC control, maybe high-end gaming.
Right.
Then you have Synchron with their Stentrode. This is the least invasive approach. It's inserted endovascularly through the jugular vein, so it prioritizes basic digital access with a lower channel count.
And now Paradromics comes in as the clear performance leader. They're targeting the absolute highest bandwidth, that 200 plus BPS, for the most challenging application out there, which is speech restoration.
And this is where we have to ask a really critical question. Wait a minute. If Synchron has the least invasive approach, isn't that the ultimate path to mass adoption, even if Paradromics hits higher performance first? Is performance truly the most important thing for most patients?
That's a fundamental point of friction in the industry, isn't it? For a patient who has lost all ability to communicate, someone with advanced ALS, for example, performance is paramount. They need fluid conversation, not just a slow typing tool. So they're willing to trade the invasiveness of a craniotomy for that functional outcome of communication.
So Paradromics is betting on the necessity of restoration over the convenience of a less invasive approach.
Exactly. But for a user who's just seeking, say, mental augmentation or basic text control, the safety profile of a non-invasive or an endovascular approach is almost certainly going to win the mass market over the next 5 years.
That tension is key. And speaking of non-invasive, we have to mention the parallel development our research team noted. It confirms that these BCI breakthroughs don't always require surgery.
Right. The sources corroborated a significant non-invasive breakthrough. This one involved the VA healthcare system, Carnegie Mellon, and the University of Pittsburgh.
Yeah, they demonstrated an EEG-based system. So that's just a non-invasive cap with 64 electrodes on it. And it allowed volunteers, including post-strike patients, to control robotic arms for precise point-and-click object manipulation.
So while the bandwidth is much, much lower than Kenexus, the functional result is genuinely useful. The ability to grab, move, and place physical objects without any surgical risk.
It provides a crucial alternative pathway for users who are prioritizing safety and convenience over raw performance.
Okay, let's broaden the focus now to ethics and application, because the BCI market is not niche anymore. It is projected to more than double from about $2.4 billion this year in 2025 to over $6.16 billion by 2032.
And that's a robust 14.4% compound annual growth rate. It's driving the ethical discussions forward just as fast as the technology.
This rapid acceleration is why these discussions have become so prominent.
Absolutely. The Implantable Brain-Computer Interface Collaborative Community, the IBCICC, held a critical meeting this week, and it was focused entirely on autonomy and privacy. The core question is no longer technical, it's philosophical. Who owns the data when we connect? This data stream is the raw output of human intention, of thought.
And beyond motor restoration, the broader neural applications are expanding into things like pain management. The sources highlighted a novel wireless AI implant for chronic pain.
And this moves way beyond the old paradigm of just brute force stimulation. Traditional pain implants often just delivered constant electrical signals. This new device, it acts more like a smart thermostat for the brain.
A smart thermostat.
It continuously analyzes specific neural signals associated with pain pathways and then in real time delivers targeted ultrasound stimulation to modulate to dampen those pain signals only when it's necessary.
So it's adaptive, highly efficient, and represents a massive leap in how we manage chronic suffering with these intelligent neural interfaces.
The idea of a smart thermostat for pain, that intelligent modulation over blunt force, is actually a perfect segue into our next convergence: haptics. We're moving from that crude, singular vibration of an old pager or a smartphone notification to, well, realistic tactile simulation.
And the breakthrough that defined this week, which was corroborated across all the source material, comes from Northwestern University. They unveiled this flexible, bandage-like fingertip wearable. It's called Voxelite.
And the consensus is that this achieves the holy grail of haptics: human resolution touch.
Human resolution, that is a huge claim. The human fingertip is incredibly sensitive. So mechanically, how does Voxelite generate this realistic sensation? How does it move past the basic motors we're all used to?
It's a complete pivot away from traditional mechanics.
Yeah.
So instead of using tiny little rotating mass motors or linear actuators, Voxelite uses something called electroadhesion, which is essentially leveraging electrostatic forces. The little nodes on the patch, which sit against your skin, apply a charge that causes them to grip the skin and subtly tilt.
And that tilting motion creates a specific type of force, right?
Yes, and this is crucial. It creates shear forces, these lateral stretches of the skin, rather than just vertical pokes, which is all traditional vibration motors can deliver.
And shear forces are what our brain interprets when we feel textures.
Exactly. When you stroke a piece of velvet or run your finger across a grainy surface or feel the resistance of a button, it is absolutely fundamental to tactile perception.
So they're mimicking the natural way our skin is manipulated when we interact with the real world. What about the technical specs? What qualifies this as human resolution?
They engineered it precisely to match human acuity thresholds. The nodes themselves are spaced between 1 and 1.6 millimeters apart, which aligns perfectly with the most sensitive zones of the human fingertip.
Spatially, it's spot on.
Spot on. And temporally, it operates at up to 800 cycles per second. That covers the entire frequency range of human touch receptors, from low-frequency flutter to high-frequency vibrations.
The sources also noted the real-world performance, which is what really proves the concept. What were users able to do in the trials?
The results were stunning. Users achieved 87% accuracy, recognizing complex directional patterns, which is vital for navigation or warning signals.
And even more impressively,
they hit 81% accuracy identifying different textures, specifically real fabric textures like corduroy, leather, and terry cloth, just by using the fingertip wearable.
this truly closes the touch gap in digital environments. I mean, think about the applications beyond just gaming, which is the obvious one.
The ability to feel textures changes e-commerce entirely. You could virtually browse a carpet store or a high-end fashion catalog and get a genuine tactile preview before you buy.
And for accessibility, it's transformative.
Totally. Imagine translating real-time digital data, a complex heat map, or a 3D scan from a smartphone, into a tactile map on a user's fingertip. It would allow visually impaired users to physically experience their environment in a whole new dimension. Voxelite transforms the digital world into something physically tangible.
And complementing this fidelity in haptics is the push for form factors that literally disappear. The materials science convergence. We're talking about smart fabrics and form factors.
Yeah, the research compiled on soft robotics here is fascinating. South Korean researchers developed these ultralight fabric muzzles by weaving hair-thin, shape-memory alloy coils directly into industrial yarn.
So you can mass-produce flexible, powered actuators that just look and feel like standard fabric.
Exactly. And the sources highlight the astonishing strength packed into this lightweight material.
It's remarkable, right?
It is. In a prototype suit, and this suit weighed under 4.5 pounds, the material was shown to reduce muscle effort by over 40% during repetitive tasks, like lifting and carrying in an industrial setting.
Imagine the reduction in worker fatigue, in injury risk.
And the material itself can lift 33 pounds.
So we're looking at lightweight industrial exosuits that just blend right into standard work uniforms. But what about the medical side of this?
Well, the medical potential is profound. A lighter version of the suit was tested on patients who needed physical therapy. It improved their shoulder mobility by 57%.
So this is technology literally blending into clothing, an invisible rehabilitation suit that operates silently and subtly.
And provides assistance only when the patient's weak muscles require that support. It's restorative technology that doesn't feel like a rigid medical device at all.
And for these fabric wearables to truly disappear, they need to be durable, they need to be resilient, which leads us to the complementary work on self-healing materials.
The Penn State work here is really creative. They're using shrinkable plastic. Think of those old Shrinky Dinks toys. That's the best analogy.
Yeah.
And they combine that with a liquid gallium-indium alloy. So they create these wireless, internet-connected electronics that when you heat them, they conform perfectly to complex, three-dimensional surfaces.
So that solves the conformation problem, fitting it to the body. What about the constant stress of movement?
That's where the second development comes in. Conductive polymers that can actually self-heal. On a microscopic level, when these circuits stretch over a joint like an elbow or a knee, and the tiny conductive pathways fracture, the material automatically reforms the connection.
And that's vital for long-term wear because physical breakdown has always been the #1 failure point for wearables and clothing.
Absolutely. These breakthroughs really confirm that the invisible form factor is the inevitable future. Technology is dissolving into our environment rather than being worn as a dedicated, rigid device.
So we've covered the mind and touch integration. Now let's move to what might be the fastest moving area of consumer adoption, vision and input. Smart glasses. I mean, they've spent a decade in the trough of disillusionment, but the sources this week confirm they have officially hit their mainstream moment.
The numbers confirm the hype is justified this time. This is genuine market validation. U.S. sales of smart glasses tripled year over year in 2025.
Quadrupled. That isn't just growth, it's exponential expansion.
And the consumer adoption rate, the interest, it jumped from 20% to 25% in just 12 months. That places the technology precisely at the adoption level where smartwatches were sitting back in 2017.
Right before they became ubiquitous, this is that inflection point.
It is, and the industry is responding with unprecedented supply chain scale. EssilorLuxottica, one of the world's largest eyewear manufacturers, they're scaling production to 10 million units annually by the end of 2026.
That kind of capital commitment signals massive confidence in sustained consumer demand over the next few years.
It does. But historical distrust has been a huge issue for AR. The early days were plagued by misleading demos that just overpromised on functionality.
Which is why the formation of the AR Alliance's new laser display working group is so critical for market stability.
It is. Over 50 companies are cooperating to develop shared standards and benchmarks. They are consciously trying to establish honest performance communication to ensure mass market credibility. They're trying to address the trust barrier before it stalls adoption.
Let's look at the competitive landscape because the players are clearly targeting very specific user segments.
Meta is expanding its ecosystem with the Oakley Meta HSTN glasses, focusing squarely on the fitness and sport market.
Right. They emphasize that 8-hour battery life and seamless integration with Strava and Garmin.
Yeah, and they also showed a clever localized strategy, launching with Hindi language support in India. This shows they're treating AR as a global practical tool, not just some North American novelty.
And Samsung is signaling its aggressive entry into the market.
Yes. They confirmed details for their SMO200P glasses launching in 2026, which feature transition lenses and advanced camera functionality. The full AR display version.
Yet real competitor.
The direct competitor to the high-end players. That's slated for 2027. And meanwhile, you have brands like Vitra, which is linked to that stealth brand Vonder, challenging the premium market with AI-powered glasses targeted at a sub-$800 price point.
And that puts immense pressure on pricing across the entire board.
It does.
Now, let's talk about a convergence that has immense immediate safety implications. The automotive convergence and the intelligent cockpit.
This is a remarkable example of integration. The Chinese EV manufacturer Li Auto announced its first AI smart glasses, designed not as a standalone device, but explicitly as a peripheral for its new autonomous driving architecture, MindVLA.
Okay, let's clarify MindVLA because the critique highlighted we need to define that acronym more clearly for our listeners. What does vision language action actually mean in the context of a car?
Right. MindVLA stands for Vision Language Action. Essentially, it means the car's core intelligence system processes raw video from its cameras, vision, combines it with voice commands or instructions from the people inside, language, and then executes a move or a decision, action.
And the smart glasses add a critical fourth input stream. the driver's gaze.
Exactly. So the glasses function as a bidirectional interface with the car.
Bidirectionally. How?
So the output is the dashboard on the retina. You get AR navigation cues, speed warnings, hazard alerts overlaid directly on your field of view.
But the groundbreaking part is the input.
It is gaze tracking. The glasses monitor where the driver is looking, feeding that attention data back to the MindVLA system.
So the car knows instantly, with millisecond accuracy, if the driver is distracted, if they're looking at their phone, or if they just missed a hazard because their eyes were focused somewhere else.
This is true machine-human integration in a safety-critical system. It could potentially bridge that gap between Level 2 and Level 3 automation.
However, the sources did note that this aggressive integration faces potential regulatory friction.
It does. Authorities in China are rapidly tightening the rules around distracted driving. Regulators may end up classifying these AR glasses as a distraction, forcing Li Auto to restrict features to passengers or only allow the full AR capability when the car is parked.
That regulatory hurdle is massive, but the industry seems determined to solve the one technical barrier that killed previous AR efforts, the input problem. We all remember the awkward Google Glass days of public hand-waving.
That's the key to mainstreaming: intuitive, hands-free control. And the solution is converging on neural input bands.
Our research team noted that Wearable Devices Ltd. Completed a roadshow where major smart glasses manufacturers evaluated their Mudra neural wristband as the primary input method for their 2026 and 2027 roadmaps.
Right. And this isn't a BCI, not really, but it's adjacent. So how does the Mudra band allow for control without physical movement?
It uses surface electromyography, or SEMG. It reads the subtle electrical signals produced by your muscle movements before your fingers or hand actually move.
So it's decoding the intended gesture from the muscle signal in your wrist.
Exactly. It allows for subtle, thought-based interaction or micro-gestures, so you can select a menu item or zoom in on a map overlay just by flexing your finger muscles in a subtle way that nobody around you would even notice.
You achieve hands-free control of a complex AR environment without drawing any attention. That is the crucial missing link. The physical barriers of AR are falling because the input barrier, the one that caused all that social discomfort and usability friction, is being solved.
Okay, let's pause here for a moment because this is the perfect time for a quick break and a call to action. We've just discussed how the smart glasses market tripled and how neural interfaces are becoming the hands-free input method that will push them into ubiquity. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and continue these deep dives.
Welcome back to Tomorrow Unveiled. We've seen integration in the mind, touch, and vision. Now, let's turn to the realm where this high-bandwidth integration has the highest stakes: clinical health monitoring. This field is moving away from periodic spot checks and toward continuous, clinically relevant data streams.
Yeah, the industry's focus right now is entirely on non-invasive, continuous measurement of metrics that traditionally required cumbersome medical equipment. And the prime example is the quest for cuffless and continuous blood pressure monitoring.
The sources highlight two key research efforts accelerating this. Researchers at the University of Texas at Austin received substantial funding, $2.5 million, to integrate cuffless BP monitoring directly into a smartwatch form factor.
And their method is highly innovative. They use radio frequency, or RF, waves emitted by an integrated antenna, combined with complex machine learning algorithms. The crucial difference is this eliminates the need for any direct skin contact or the traditional optical contact.
It's measuring blood dynamics internally via RF signals.
Exactly. And at the same time, we saw corroborating research from UNC Chapel Hill that uses a different but equally promising approach.
Right. That research demonstrated a non-invasive wearable using the traditional PPG sensors, on a fingertip or toe, to measure pulse wave velocity.
But the key finding was its accuracy. It achieved medical-grade precision around a 1 millimil Hg deviation, which is incredibly close to an actual cuff measurement.
Which signifies that the holy grail of accurate, continuous BP monitoring is on the verge of being commercially viable in consumer devices.
It seems so. And for chronic conditions, the industry leader in continuous glucose monitoring, or CGM, made a significant announcement regarding the glucose challenge.
Dexcom. They announced the launch of their G7 15-day CGM system.
And while extending the wear time by just a few days might seem incremental, that 15.5-day wear time now leads the industry. This reduces monthly sensor changes, it cuts down on waste, and it's a major quality of life improvement for millions of patients.
And crucially, the system maintains a high accuracy rating of 8% RRD, which is the standard clinical benchmark. It shows the technology can be extended without sacrificing data integrity.
We also saw the maturing of regulatory pathways with key FDA clearances, like Hexaskin's medical system's SmartShirt for continuous long-term ECG and respiratory monitoring. This confirms that regulatory bodies are really establishing specific rules for complex physiological data captured outside of a clinic.
However, the sources also brought up a very necessary and very sobering point, underscoring the high stakes of all this integration through the Abbott incident.
This was a serious reminder of the immense responsibility that comes with making clinical-grade claims. Abbott issued a global medical device correction for its Freestyle Libre 3 and Libre 3 Plus sensors.
What was the root cause of that?
The failure was traced to a specific production line issue that resulted in incorrect artificially low glucose readings.
And when a sensor gives a false low, a patient might overcorrect by consuming sugar, leading to a potentially dangerous high.
Exactly. And the scale of this issue was staggering. 736 severe adverse events reported globally, and 7 deaths potentially associated with the incorrect readings.
Affecting approximately 3 million U.S. sensors. This goes far beyond a typical consumer electronic recall.
It really does. The core insight here is that the production process for these integrated health devices must meet true pharmaceutical-grade quality standards. The systemic failure revealed by this incident is that even a slight deviation in a high-volume manufacturing process can have life-or-death consequences downstream.
So this incident served as a wake-up call, potentially leading to specific new mandates regarding hardware verification protocols during mass recalls of medical wearables.
It had to. On a positive note, though, this severity highlights the value of continuous data in a clinical setting. And we can see that in the hospital transformation being driven by continuous monitoring.
The rollout story from Netcare, a major South African hospital group, is a perfect illustration of this.
Yeah, they announced the global deployment of medical-grade wrist wearables, the Corsano Health Cardio Watch, across 6,000 beds.
Why is that scale so significant?
Because it fundamentally changes the economics of patient care. It shifts monitoring from those periodic spot checks, which happen every 4 to 6 hours, to 247 continuous surveillance. For the vast majority of their stay, patients used to be unmonitored. Now they're watched constantly by a sophisticated system.
And what is the AI system watching for that a human might miss? What are the biomarkers they're targeting for early detection?
So the system is primarily focused on detecting sepsis and cardiac arrest hours before it would be visible to a human. The AI is continuously tracking a complex baseline profile. Minute by minute, heart rate variability, subtle changes in respiratory patterns, core body temperature, and continuous peripheral perfusion data.
Which is basically how well blood is reaching the extremities.
Right, and these multiple data streams, when the AI algorithms combine them, can detect that subtle hours-long deviation that precedes a severe event like sepsis. It allows for intervention before the patient reaches a critical state.
That's not only a clinical win, saving lives, but an economic one, drastically reducing costly ICU readmissions. As we've seen, the consequences of deep integration are high, whether it's through hardware failure or data exploitation. As this technology moves closer to the body and the mind, the friction points around privacy and security become the defining challenge for mass adoption.
That tension is driving a rapid regulatory reckoning, particularly focused on closing what our team calls the Hypa gap.
And the privacy crisis is simple. Health data collected by your doctor is protected by Hypa. You have legal control over that information, but the exact same intimate health data, your biosignals, your location, your sleep patterns, collected by a consumer device like an Oura Ring or a Fitbit,
It's currently not protected by Hypa.
and that data, because it lacks that protection, can be sold openly to data brokers, to insurers, to marketing firms without your consent or control. It's a massive and dangerous legislative loophole.
It is. The legislative response noted in the source material is the introduction of the Health Information Privacy Reform Act, SB 3D097.
And this bill is designed explicitly to close that gap.
Yes. If it passes, it would redefine applicable health information to specifically include data generated by consumer wearables. This would mandate high PA-level protection for all of that continuous data.
So what would the market impact be if this actually passed?
It would fundamentally alter the economic model of the cheap wearable.
Hmm.
Companies could no longer rely on monetizing raw user data as their main revenue stream. Instead, it would push the entire industry toward a subscription model where the user pays a premium for privacy.
Or a subsidized model where data is only anonymized and aggregated.
Right, stripping it of its individual value. It would be the end of the cheap wearable that sells your secrets to keep costs low.
And at the same time, we saw the FDA signaling increased oversight, moving aggressively to draw a hard line between wellness and medical claims.
That's the warning letter they issued regarding a blood pressure insights feature on the WUPA wearable. The FDA is arguing that estimating BP, even if you vaguely position it as an insight, constitutes a diagnostic function.
And why does that matter legally?
Because if it's a diagnostic function, it requires the rigorous 510(k) medical device clearance. For our listeners, a 510(k) is the FDA process that mandates a company prove its new device is as safe and effective as a legally marketed device that's already out there.
It's a costly, time-consuming process that ensures the device has scientific merit and validated accuracy.
So the FDA is essentially saying you can no longer hide medical functionality behind a wellness disclaimer.
Exactly. This action establishes a critical hard line. Companies either have to clinically validate their claims through the 510(k) process and accept the intense scrutiny that follows, like the risk of an Abbott-style incident, or they have to strip the features entirely.
This will clearly bifurcate the market between regulated medical technology and just basic activity trackers.
Policy and regulation are racing to catch up, but technology itself is also offering solutions to the privacy challenge through edge computing.
And this is really a matter of necessity meeting utility. For high-bandwidth, low-latency applications like the Kenexus speech restoration or the Li-Auto MindVLA system, you cannot afford the delay of sending all that data to the cloud for processing.
So processing must happen at the edge, meaning on the device itself or a very local hub.
Right. And this edge AI serves the crucial dual purpose of speed and privacy and efficiency.
How so?
Well, edge AI allows sophisticated anomaly detection, identifying a cardiac arrhythmia, or detecting an imminent fall to happen locally. The system processes 99% of the raw, intimate data on the device and sends only the specific alert, warning, sepsis imminent, to the cloud.
So it protects the raw, continuous data stream, greatly increasing privacy while ensuring instant responsiveness.
Exactly. But once that data needs to move, even if it's just the alert, it still needs security. And wearables have tiny batteries. Traditional banking-grade encryption must be way too power-intensive for an implant or a smart ring.
That brings us to the crucial layer of invisible security. New research published this week focuses on what are called lightweight sign encryption schemes, comparing protocols like SPEC and PRESENT.
And can you give us an analogy for why these are needed over traditional encryption methods like AES?
Sure. Think of traditional encryption, like what secures your banking app, as a high-security, custom-built steel vault. It's incredibly strong, but it takes massive computational power or material to open and close it, constantly draining your battery.
Okay.
These new lightweight sign encryption schemes are like designing a microscopic vault using advanced, highly efficient composite materials. They offer the same verifiable integrity and strong encryption, but with 100 times less computational material.
Dramatically reducing the power drain on those tiny batteries.
It's the essential invisible security layer required to secure that continuous, high-fidelity data stream without constantly needing a recharge.
Before we wrap up with our final thoughts on convergence, we want to make sure you know how to stay connected with Tomorrow Unveiled and the community.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this new era of human-computer integration. Are you ready to be strapped in?
The week of November 19th through 26th, 2025, wasn't defined by a single gadget launch. It was defined by systemic convergence. This is the so what of the strapped-in era.
We saw three main areas where integration accelerated dramatically, marking a true structural shift. First, the brain. High-bandwidth BCI moving toward functional speech restoration, demonstrating that critical 200 BP's data transfer capability.
And that performance versus invasiveness debate is now central to the whole BCI race.
Second, touch. Haptics that are scientifically proven to match human sensory resolution. The Voxelite system, using electroadhesion and shear forces, proves we can now feel textures in the digital world, closing that touch gap for AR and VR.
And third, vision and input. Smart glasses hitting the mainstream adoption threshold with that crucial usability barrier hands-free input being solved by subtle neural band controllers like the SEMG Mudra Band.
enabling practical use in high-stakes environments like autonomous vehicles.
And the unifying theme is this: technology is no longer external. It is merging with our bodies and our minds. We have BCIs connecting to neural tissue, smart fabrics dissolving into our clothing, haptics matching our sensory resolution.
And clinical sensors providing continuous life-saving data streams.
Looking ahead to 2026 and beyond, our research team identified three inevitable near-term shifts. First, AR mainstreaming is going to accelerate rapidly.
If manufacturers hit their scale goals, EssilorLuxottica aiming for 10 million units, Samsung delivering its AR display versions, smart glasses will become ubiquitous, particularly because that neural input challenge has been demonstrably solved.
Second, expect medical accuracy to be the new table stakes. Continuous, non-invasive monitoring like cuffless BP will likely become standard features in next-gen consumer smartwatches and rings.
But this democratization of medical data is going to intensify regulatory scrutiny across the board, forcing wellness brands to prove their claims or face FDA intervention.
And finally, the Disappearance Act. Advances in soft robotics, shape memory alloy fabrics, and self-healing polymers, combined with the efficiency and privacy of edge AI, will make wearables physically and computationally invisible.
They will dissolve into clothing or skin-like patches, operating locally for both speed and privacy.
We've seen technical breakthroughs this week that could restore speech, prevent hospital deaths, and give us a richer, tactile digital life. But these breakthroughs demand intimacy and data control.
And the research team observed that the technical barriers, the ability to seamlessly connect our minds and bodies to the digital world, are falling faster than the trust barriers, our ability to ethically manage that data and guarantee its privacy.
So the question becomes,
If governments and regulators ultimately require us to wear high-fidelity health tracking devices for preventative care, and this is being actively discussed in some health agendas, will the immense societal benefit outweigh the complete surrender of digital privacy and autonomy? What price are you willing to pay to be truly strapped in?
a truly profound tension that will define the rest of this decade.
Thank you for joining us for this deep dive on Tomorrow Unveiled. We'll see you next week.